So how do we learn? And why do some of us learn things more easily than others? So as I was mentioned, I'm Dr. Laura Boyd. I'm a brain researcher here at the University of British Columbia. And these are the questions that fascinate me. So brain research is one of the great frontiers in the understanding of human physiology, and also in the consideration of what makes us who we are. It's an amazing time to be a brain researcher, and I would argue to you that I have the most interesting job in the world. What we know about the brain is changing at a breathtaking pace. And much of what we thought we knew and understood about the brain turns out to be not true or incomplete. Now, some of these misconceptions are more obvious than others. For example, we used to think that after childhood, the brain really could not change. And it turns out that nothing could be farther from the truth. Another misconception about the brain is that you only use parts of it at any given time, and it's silent when you do nothing. Well, this is also untrue. It turns out that even when you're at rest and thinking of nothing, your brain is highly active. So it's been advances in technology, such as MRI, has allowed us to make these and many other important discoveries. And perhaps the most exciting, the most interesting and transformative of these discoveries is that every time you learn a new fact or skill, you change your brain. It's something we call neuroplasticity. So as little as 25 years ago, we thought that after about puberty, the only changes that took place in the brain were negative. The loss of brain cells with aging, the result of damage, like a stroke. And then studies began to show remarkable amounts of reorganization in the adult brain. And the ensuing research has shown us that all of our behaviors change our brain, that these changes are not limited by age. It's good news, right? And in fact, they're taking place all the time. And very importantly, brain reorganization helps to support recovery after you damage your brain. The key to each of these changes is neuroplasticity. So what does it look like? So your brain can change in three very basic ways to support learning. And the first is chemical. So your brain actually functions by transferring chemical signals between brain cells, what we call neurons, and these trigger a series of actions and reactions. So to support learning, your brain can increase the amount or the concentrations of these chemical signaling that's taking place between neurons. Now, because this kind of change can happen very rapidly, this supports short-term memory, or the short-term improvement in the performance of a motor skill. The second way that the brain can change to support learning is by altering its structure. So during learning, the brain can change the connections between neurons. Now here, the physical structure of the brain is actually changing, so this takes a bit more time. These types of changes are related to long-term memory, the long-term improvement in a motor skill. Now, these processes, they interact, and let me give you an example of how. So we've all tried to learn a new motor skill, maybe playing the piano, maybe learning to juggle. And you've had the experience of getting better and better within a single session of practice and thinking, I've got it. And then maybe you've returned the next day and all those improvements from the day before, they're lost. What happened? Well, in the short term, your brain was able to increase the chemical signaling between your neurons. But for some reason, those changes did not induce the structural change that are necessary to support long-term memory. Remember that long-term memories take time, and what you see in the short term does not reflect learning. It's these physical changes that are now going to support long-term memories and chemical changes that support short-term memories. Structural changes also can lead to integrated networks of brain regions that function together to support learning. And they can also lead to certain brain regions that are important for very specific behaviors to change their structure or to enlarge. And so here's some examples of that. So people who read Braille, they have larger hand sensory areas in their brain than those of us who don't. Your dominant hand motor region, which is on the left side of your brain if you're right-handed, is larger than the other side. And research shows that London taxi cab drivers who actually have to memorize a map of London to get their taxi cab license, they have larger brain regions devoted to spatial or mapping memories. Now, the last way that your brain can change to support learning is by altering its function. As you use a brain region, it becomes more and more excitable and easy to use again. And as your brain has these areas that increase their excitability, the brain shifts how and when they're activated. With learning, we see that whole networks of brain activity are shifting and changing. So neuroplasticity is supported by chemical, by structural, and by functional changes. And these are happening across the whole brain. They can occur in isolation from one another, but most often they take place in concert. Together, they support learning, and they're taking place all the time. So I've just told you really how awesomely neuroplastic your brain is. So why can't you learn anything you choose to with ease? Why do our kids sometimes fail in school? Why, as we age, do we tend to forget things? And why don't people fully recover from brain damage? That is, what is it that limits and facilitates neuroplasticity? And so this is what I study. I study it specifically how it relates to recovery from stroke. So recently, stroke dropped from being the third leading cause of death in the United States to be the fourth leading cause of death. Great news, right? Well, it actually turns out that the numbers of people having a stroke has not declined. We're just better at keeping people alive after a severe stroke. It turns out to be very difficult to help the brain recover from stroke. And frankly, we have failed to develop effective rehabilitation interventions. The net result of this is that stroke is the leading cause of long-term disability in adults in the world. Individuals with stroke are younger and tending to live longer with that disability. And research from my group actually shows that the health-related quality of life of Canadians with stroke has declined. So clearly, we need to be better at helping people recover from stroke. And this is an enormous societal problem, and it's one that we're not solving. So what can be done? One thing is absolutely clear. The best driver of neuroplastic change in your brain is your behavior. The problem is that the dose of behavior, the dose of practice that's required to learn new and relearn old motor skills, it's very large. And how to effectively deliver these large doses of practice is a very difficult problem. It's also a very expensive problem. So the approach that my research has taken is to develop therapies that prime or that prepare the brain to learn. And these have included brain stimulation, exercise, and robotics. But through my research, I've realized that a major limitation to the development of therapies that speed recovery from stroke is that patterns of neuroplasticity are highly variable from person to person. Now, as a researcher, variability used to drive me crazy. It makes it very difficult to use statistics to test your data and your ideas. And because of this, medical intervention studies are specifically designed to minimize variability. But in my research, it's becoming really clear that the most important, the most informative data that we collect is showing this variability. So by studying the brain after stroke, we've learned a lot, and I think these lessons are very valuable in other areas. So the first lesson is that the primary driver of change in your brain is your behavior. So there's no neuroplasticity drug you can take. Nothing is more effective than practice at helping you learn, and the bottom line is you have to do the work. And in fact, my research has shown that increased difficulty, increased struggle, if you will, during practice actually leads to both more learning and greater structural change in the brain. The problem here is that neuroplasticity can work both ways. It can be positive. You learn something new and you refined a motor skill. It also can be negative, though. You forgot something you once knew. You become addicted to drugs. Maybe you have chronic pain. So your brain is tremendously plastic, and it's being shaped both structurally and functionally by everything you do, but also by everything that you don't do. The second lesson we've learned about the brain is that there is no one-size-fits-all approach to learning. So there's no recipe for learning. Consider the popular belief that it takes 10,000 hours of practice to learn and to master a new motor skill. Now, I can assure you it is not quite that simple. For some of us, it's going to take a lot more practice, and for others, it may take far less. So the shaping of our plastic brains it's far too unique for there to be any single intervention that's going to work for all of us. And now this realization has forced us to consider something called personalized medicine. So this is the idea that to optimize outcomes, each individual requires their own intervention. And the idea actually comes from cancer treatments. And here it turns out that genetics are very important in matching certain types of chemotherapy with specific forms of cancer. My research is showing that this also applies to recovery from stroke. So there are certain characteristics of brain structure and function that we call biomarkers. And these biomarkers are proving to be very helpful in helping us to match specific therapies with individual patients. And the data from my lab suggests it's a combination of biomarkers that best predicts neuroplastic change and patterns of recovery after stroke. And that's not surprising given how complicated the human brain is. But I also think we can consider this concept much more broadly. Given the unique structure and function of each of our brains, what we've learned about neuroplasticity after stroke applies to everyone. Behaviors that you employ in your everyday life are important. Each of them is changing your brain. And I believe we have to consider not just personalized medicine, but personalized learning. The uniqueness of your brain will affect you, both as a learner and also as a teacher. And now this idea helps us to understand why some children can thrive in traditional education settings and others don't, why some of us can learn languages easily, and yet others can pick up any sport and excel. So when you leave this room today, your brain will not be the same as when you entered this morning. And I think that's pretty amazing. But each of you is going to have changed your brain differently. Understanding these differences, these individual patterns, this variability and change, is going to enable the next great advance in neuroscience. It's going to allow us to develop new and more effective interventions and allow for matches between learners and teachers and patients and interventions. And this does not just apply to recovery from stroke. It applies to each of us as a parent, as a teacher, as a manager, and also, because you're at TEDx today, a lifelong learner. Study how and what you learn best. Repeat those behaviors that are healthy for your brain, and break those behaviors and habits that are not. Practice. Learning is about doing the work that your brain requires. So the best strategies are going to vary between individuals. You know what? They're even going to vary within individuals. So for you, learning music may come very easily, but learning to snowboard, much harder. I hope that you leave today with a new appreciation of how magnificent your brain is. You and your plastic brain are constantly being shaped by the world around you. Understand that everything you do, everything you encounter, and everything you experience is changing your brain. And that can be for better, but it can also be for worse. So when you leave today, go out and build the brain you want. Thank you very much.